So this is our sequential circuits topic. Under the sequential circuits topic, we have the storage element. A sequential circuits consists of a combinational circuit and a feedback circuit. These feedback circuits are also called the storage element. The outputs can depend on present and also past values of the input and output variables. Then these output move sequentially through a defined sequence of transition from one state to the next. These output variables are used to describe the state of the sequential circuit, either directly or deriving state variables for them. So what are the contents of the storage element? It is a collection of known internal signals values that contains information about the past necessary to account the future behavior of the circuits. So these are the current state. It is the state of the memory element at present. The next states are function of inputs and present states of storage element, and the clock signals a square wave of fixed frequency. Transition will occur on one of the edges of the clock pulses. So there are two types of sequential circuits. We have synchronous and asynchronous. So this is the synchronous circuits. We have a combinational circuit, then we have our feedback elements, which is your memory elements, and we have another input for your memory elements, which is your clock pulse. So the timing of all transition is controlled by a common clock. Changes in all variables occur simultaneously, and it is easier to design. The second one is what you call your asynchronous circuit. So we have no more inputs to your memory elements. State transition occur independently of any clock and normally dependent on the timing of transition in the input variables. Changes in more than one output do not necessarily occur simultaneously. This type of circuit may have better performance but hard to design. So for the storage element, we have the LUTs, a level-sensitive memory element which include RS and DLUTs. And we have the flip-flop, usually an edge-triggered memory elements. Under flip-flop, we have J key, T flip-flop, and master sleeve flip-flop. So we begin our discussion with the LUTs. So you can recall the transistor switching. So this is our circuits in our transistor switching. We have two transistors connected in back-to-back. So the transistor has different saturation delete time. So we have no equal transistor delete time in all your transistors. They are different. They have different delete time. So if Q1, so we have transistor 1 and transistor 2 in your right side, transistor 1 in your left side. If Q1 saturate first, then Q2 is in cutoff. If we see saturate, the voltage from collector to emitter, so this one going to your emitter, is almost equivalent to 0. So we have a supply to your transistor 2 to the base is almost equivalent to 0. That's why your transistor 2 is in cutoff state. Then the value of your Q, it is grounded because your transistor 1 is in saturation, so therefore it is equivalent to 0, and your Q bar is equivalent to VCC because it is cut off. So if transistor 2 saturates first, then Q1 is in cutoff state. The value of Q is equivalent to BCC or 1 and Q bar is equivalent to 0 or it is grounded. So it will remain in this state. The output is latched on that particular value unless there will be any interference at the base of the transistor. So we have to connect two input in the base of your two transistor. We have R and S. R is connected to the base of Q1 and S is connected to the base of Q2. So solving for this one using table, we have input R and S. We have the state of your transistor 1 and transistor 2, then your output Q and Q bar. So we begin our input between your R and S as 0 and 1. 0 means it is connected to the ground and 1 it is connected to a BCC. So since S is connected to a BCC and it is connected to the base of the transistor 2, therefore transistor 2 will saturate. And since your base of your transistor 1 is connected to the ground, then it is cut off. If Q2 is in saturation state and Q1 is in cut-off state, so therefore Q is equivalent to 1 and Q bar is equivalent to 0. If we have to interchange the input, if we have R is connected to BCC and S is connected to the ground, so it means transistor 1 is in saturation state and transistor 2 is cut off, making your Q equals to 0 and Q bar equals to 1. When both transistor base is connected to ground, so if it is connected to ground, what is the state of the transistor? It will remain. So we have transistor 1 will not change, transistor 2 also will not change. Your output is no change. If they are connected to both BCC, your R and S, so it means that these two transistors will saturate, but who will be the first to saturate? So we don't know because we don't know the transistor delay time. So we call that one as a race condition. So therefore, R, as you can see in your table, when R is equivalent to 1, your Q is 0. So it means it is reset. When S is equivalent to 1, then your Q is equals to 1. So S is set. So first latch that we have is the RS latch. Can be either constructed with two cross-coupled NOR gates or two cross-coupled NAND gates. For a NOR latch or NOR RS latch, we have this one. So we have to determine the functionality table. So we have your previous output Q, we call that one as QP, your input R and S, your gate 1 is 1, and this is your gate 2. Then we have to solve for the next value of your output, or we call this one as QP plus 1, or next value of your Q after inputs occur. But remember what is the output of your NOR. So the truth table of your NOR. So in the truth table of your NOR, you have your input A and B. If you have 0, 0, that is 1, 1, 0, or 0, 1, that is 0, 1, 0, it is 0, 1, 1, it is 0. As you can observe, if one of the input of your NOR is 1, either the second input is 0 or 1, you have an output of 0. So for the functionality table, if our previous output is 0 and your input R and S is also 0, so we have to determine your output of these two transistors. So if your previous output is 0 and your S is also 0, then if we have to perform the NOR truth table of 0 NOR 0, so your NOR 2 is equivalent to 1 and your NOR 1 is equivalent to 0 because the output of your NOR 2 is 1, NOR 8 with 0, therefore it is 0. So Q P plus 1 or the next value of our Q which is connected to your NOR 1, it is equals to 0. If we have 0 and 1, 0 for R, 1 for your S. So as you can recall in our previous slide of your NOR truth table, if one of the input of your NOR is equivalent to 1, then the output is 0. So since the input of our S is 1, your Q bar will be 0. If Q bar is 0, then your S is 0, then your R is 0. So we have to NOR these two, then we have an output of your 1 equals to 1, your 2 is 0, so therefore Q plus 1 is 1. Then for 1 0, for 1 0, R is 1, S is 0. Since your R is 1, we have an output of your Q equivalent to 0. 0 NOR with 0, then it is equals to 1. So we have 1 for your 2 and 0 for your 1. Then for 1 1. So when this is equivalent to 1 and this is also equal to 1, both output must generate a 0. But which of these two NOR gate will generate first the 0? So we don't know. So we call that one as race condition. Then for our Q or present value of our Q is 1, then we begin with your input 0 0. So this is 0 and this is also 0. So since this is 0 and this is 0, so we have to determine that output from the previous Q. So we have to get the Q value which is 1. If this is 1, then S is 0. We have to NOR this 1. You got an output of 0. 0 NOR with 0, then it is equals to 1. So we have your NOR 1 equals to 1 and NOR 2 is equals to 0. So therefore your QP plus 1 equals to 1. For 1 0 1, so your S is 1. So if this is equals to 1, even though which second input is either 0 or 1, we will generate an output of 0. If this is 0, then this is also 0 for your R, so 0 NOR 0 equals to 1. So your 1 NOR 1 is 1, your NOR 2 is 0, so therefore your output is 1. Then for 1 0, so now it is equals to 1 for your R. If R is 1, your output of your NOR 1 is equivalent to 0. 0 NOR with 0 for your S, so output of your 2 is equals to 1. So we have 0 for 1, then for 2 is 1, then your QP plus 1 is 0. Then if they are both 1 1, so this is the same as your previous mean. Both input of your NOR gate is 1 1. One input here is R is 1, so it will generate an output of 0. Then if it is also 1 here, so in your S, this also will generate an output of 0. So we don't know which of the two NOR this will first generate an output of 0. So therefore it is a race condition. So we have this input R and S which is 0, 0. And your previous output or your QP it is 0, then you have an output of 0. And if it is 1, so that is no change as you can see. And if it is 1, then you have an output of 1. That is also no change. Then for the combinations 0 and 1, if your QP is 0, then you have 0 and then the second QP is 1, both output is equals to 1. And if we have a combination of 1, 0, then your QP 0 or 1, you have an output of 0. And if it is 1, 1, then we have a race condition. So therefore, our truth table for this one is equivalent to, for R and S 0, 0, that is no change. For 0, 1, then your Q is 1. If your R is 1 and your S is 0, then your Q is equals to 0. If both input R and S is 1, we have a race. So this is your circuit diagram, and this is what you call your logic symbol. So the truth table of your storage element, it will map the current state and inputs to output. For the non-RS latch, so we have the same functionality table. You have the QP, it is the present value of Q. We have input R and S. We have the non-1 and the non-2. Our output will be called QP plus 1 or the next value of Q. So recall your truth table of your NAND gate. So in your NAND, if we have 0, 0, we have 1. If we have 0, 1, it is also 1. 1, 0, that is also 1. But if we have both input or 1, then you have an output of 0. As you can observe, when you have an input of 1, one of the input of your NAND is 0, you will generate an output of 1. So back to your functionality table. If your QP is 0, R is 0, and S is 0, so we have here 0, and this is 0, then we'll be having a race condition of your output. Recall in your truth table of your NAND gates, if one of your input is 0 and this is also 0, if it is 0, it means that it will generate a value of 1. If this is also 0, it will generate a value of 1. So we don't know which of these NAND gate will generate first a value of 1. So we call that one as race condition. Then for 0 and 1. So since your R is equivalent to 0, if this is 0, remember in your NAND, if one of the inputs of your NAND is 0, then you have an output 1. So since this is 0, then we have the output of your first NAND equals to 1. And the second output of your NAND 2 or the output of your second NAND will be equivalent to 0. So Q plus 1 is 1. Then for input, R is 1 and 0 for S. So we have to begin with S equivalent to 0. If this is equals to 0, then we have an output here equivalent to 1. 1 NAND 1 is 0. So therefore, we have 0 for your NAND 1 and 1 for your NAND 2. Then for input, 1, 1. So for input 1 and 1. So if this is 1 and this is 1, so we have now to determine the second input of your NAND. At your Q, this is 0. If we have 0, NAND with 1, it is equals to 1. 1, NAND with 1, this is equals to 0. So your previous Q is 0. So therefore, it is equals to 0, 1, 0. Then, if we have 0, 0, so since both input of your R and S is 0, then we have a raise. Then if we have 0, 1, so since R is 0, your first NAND gate will generate an output of 1. If this is 1, so the second NAND gate will generate an output of 0. And if we have 1, 0, so since this is 0, your second NAND gate will generate an output of 1, and your first NAND gate, since this is 1, then we have to NAND this with 1 for your R, so your first NAND gate will generate an output of 0. And they are 1, 1, so if this is 1, your S is 1, and your R is also 1, so both input of your gate 1 is 1 and gate 2 is 1, then the output of these two NAND gates must generate an output of 1, an output of either 0 or 1. So we have first to determine your value of your Q. Since Q equals to 1, NAND this with 1 for your S, we have your Q bar equivalent to 0. If this is 0 at your Q bar, then your R is 1, NAND that 2 inputs, then your Q will be equivalent to 0, to 1. So we have 1, 0, 1. So if your input are all 0, we have arrays. And if your combination of your input 0 and 1, it's either your previous Q or your QP is 0 or 1, you have an output of 1. If you have a combination of your input 1 and 0, and your previous Q or your QP is either 0 or 1, you have an output of 0. But if your combination is 1, 1, and if your previous is 0, your output is the same, 0. If your previous is 1, your output is 1. So that is what you call your no change. So therefore, your truth table, if we have for R and S 0, 0, we have a raise. If your R is 0 and your S is 1, we have 1, 0. If your R is 1, then S is 0, then you have 0 and 1. If both input are 1, 1, so we have no change. So this is your logic symbol, and we have that circuits diagram. So for a level clocking nor RS loss. So we have now a third input. We call that one as your clock. So we have to get your truth table. So if your clock is equivalent to 0, so if your clock is equivalent to 0, either your R and S has a value of 0 or 1, the output of this AND gate are all 0. So since this is a NOR gate, if they are all 0, therefore we have no change in your output. Then for your clock is equivalent to 1, and your both input R and S are all 0, then the NAND gate output are also 0. So we have no change. Then if your S is equivalent to 1, so we have an output of your second AND gate equals to 1. Since your second AND gate is 1 and your first AND gate is 0, so therefore we have an output of 1 and 0. Then if we have 1 and 0 for your R, so the first AND gate is 1, so therefore we have an output of 0 and 1. And if they are both 1, 1, so therefore we have a race condition. So this is the symbol or logic symbol of your level clocking NOR RS. For level clocking non-RS, so the third input is your clock and it is connected to an AND gate. So we have this truth table, clock RS, then your output Q and Q bar. So if your input is 0 and your R and H is either 0 or 1, so we call that one as X. So the output of your NAND gate is 0. So remember, in your NAND RS, if we have input 0, 0, then it is a race condition. Then if we have 1 and 0, 0 for your R and S, so therefore the result or the output of your AND gate are also 0. So that is race condition for your output in your NAND gate. If you have 0 and 1, so the second AND gate will generate an output of 1. This will cause your NAND gate 2 to have an output of 0, and since it is 0, we have to NAND that 1 with 0, then we have a 1. Then if we have 1, 0, so your second AND gate is 0 and your first AND gate is 1. Then if it is 0, remember in your NAND, if we have 0, one of its input, then it will generate an output of 1. 1 NAND with 1 is equals to 0. So therefore your Q is 0 and 1 for your Q bar. And if it is 1, 1, so we have both input 1 and 1, then it means it is a no change. And we have this logic symbol. So for the edge-triggered RS latch, in your input side, we have the RC network connected. You have to determine your truth table. If your clock is equivalent to 0, and your input are all either 0 or 1, since this is 0, your AND gate will result both AND gate will result an output of 0. So we have no change. If it is equivalent to 1, and either X is 0 or 1 and S is 0 or 1, you will generate an output of your 2 AND gate equals to 0. So since this is edge triggered and this is your R, so it is look like this one. So during negative, and this is your clock input. So when your clock changes state from 0 to 1, your capacitor will charge the value of this 1. But since it is directly connected to the ground, it will discharge directly to 0. So it means that when your input is equals to 1, this is equals to 1 or label 1, so we have a component of your value that will go to your AND gate. It has a 0. So it means your output of your AND gate are all 0 because of this condition. So therefore, since it is connected to your NOR, and that is no change. Then if we have going down, so if it is going down, this one going down, so that is your going down. So that is also no change. And if it is going up, then we have 0, 0 as your input. So therefore, the result or the output of your two AND gate are also 0. So that is no change. If we have still going up, and your S is 1, and your R is 0, so since S is equivalent to 1 and your R is 0, so remember in your NOR, when one of the input of your NOR is 1, you have an output is equivalent to 0. So if it is 0, your output of this NOR is 0. 0, NOR 0, then your Q will be equivalent to 1. Then if it is 1, 0, so if it is 1, 0, since this is 1, so your Q will be 0, making your Q bar to 1. And if they are 1, 1, so these two NAND gate, NOR gate will generate an output of, so if it is 1, 1, remember if you have a 1, 1, 1, 1, it will generate an output of 0. So either, so it will generate an output of 0 on both sides, but we have to determine that one using your Q. So your Q, since there will generate an output of 0, then we don't know which of these two NOR gate will generate first, so we call that one as race condition. So this is your circuit diagram, and that is your logic symbol. Then we have the D-latch. This can be constructed with two cross-coupled NOR gates. So we have this functionality table. So your QP, that is your presence value of Q, your QP plus 1, that is your next value of your Q. So if you have 0, 0, so the output of your inverter is 1. So this will make your first NOR gate equals to 1, equals to 0, and your second NOR gate equals to 1. So we have an output of 0. If we have D equals to 1, so your output of your inverter is 0. We have 1, this make your Q bar equals to 0 and making your Q equals to 1. If it is your previous output is 1 but your D is 0, that will make your first NOR gate equals to 0 and your second NOR gate equals to 1. If your input is 1, this make your second NOR gate equals to 0 and your first NOR gate equals to 1. So this is your truth table. So as you can see, your output will only follow what is in your input. So for the level clocking D, so we have to connect an AND gate to the input of your NOR. So If we have a clock equivalent to 0, then your output of your 2 AND will be 0. So since it is 0, that is no change. If we have a clock equivalent to 1, then we have to first determine your input D. So if D is 0, then the first AND gate will generate an output of 1. Since 1 in your first AND gate, this is 1, and this is 0. Since this is 1, it will generate an output here equivalent to 0, and making your Q bar equals to 1. And if we have 1, 1, if this is 1, so this is 0. So we have 1, we have an output here equals to 1, making your NOR gate 2 equals to 0, 0, NOR with 0, then your NOR gate 1 equals to 1. So this is your truth table. So if your clock is 0, that is no change. If your clock is 1, then your Q will follow what is in your D. So that is, D is to eliminate the race condition of your RS. For the H trigger D, we have your RC network connected at the clock. So during 0 clock, your input is either 0 or 1. The output of your 2 AND gate are all 0. So we have no change. If your clock is 1, so either 0 or 1 is your D or your input D, then your output of your 2 AND gates are all 0, then we have no change for your output of your NOR. If your clock is going down, your input is either 0 or 1. Your output of your 2 AND gate are all 0, then that is no change for your NOR. And if your clock is going up and your D is 0, so the output of your first AND gate will generate a 1. If it is equals to 1, then the first NOR will generate an output of 0, and your second NOR will generate an output of 1. Going up, and your input is 1. This will make your second AND gate to generate an output of 1. Since it is equals to 1, this NOR gate, the second NOR gate, will generate an output of 0. If this is 0, NOR with 0, then your first NOR will generate a 1. So this is your circuit diagram, and this is our truth table. This is also your logic symbol. Then for flip-flops, we have the JK. So this is the circuit of your JK. You have your input, your Q, that is your QP, that is your previous Q, then input key and J, and you have the next value of your Q. So we have to consider that the clock is at 1. So if both input and your clock and your Q is 0, you have an output of 0 for your AND gate. Since it is 0, so we have your QP plus 1 is also equals to 0. So this is 0, NOR with 0, it is equals to 1. 1, NOR with 0, that is also equals to 0. Then, if we have K0 and 1 for your J, so you have an output of 1 in your second AND gate and 0 in your first AND gate. So since it is equals to 0, it is connected to one of the input of your NOR, this will This is NOR with this 0 and this is 1 with this connected to another. So the second input of your NOR. So since it is 0, so we have to determine first what is the second input of your NOR. But since it is equivalent to 1, this NOR will generate an output of 0. If this is 0, now we have a second input of your first NOR as 0. So we have 0, NOR 0. So that is equals to 1. And if we have 1, 0. So if it is 1, 0, then we have both input for your NOR are all 0. So we have to determine your output using the previous value of your Q. If your Q is 0, NOR 8 with 0, this is equals to 1. 1, NOR 8 with 0, this is equals to 0. So therefore we have an output of 0. And if we have 1, 1. If that is 1, 1, we have your second AND gate has a value of 1 or an output of 1. Your first AND gate has a value of 0. Since it is 1, your second NOR gate will generate an output equivalent to 0 because it is 1. So 0, NOR 0, we have a 1. The next, if your Q is 1, and both input are all 0, so therefore we have an output of your 2 AND gate are all 0. So since they are all 0, so we have now to determine your output of your NOR using your Q. So since Q equals to 1, NOR with 0, then it is equals to 0. 0, NOR with 0, then you have a 1. The next, 0, 1, if it is 0, 1, you have an output of 0. So 0, and this is 0, so we have to determine using your Q. If this is 1, NOR with 0, this is equals to 0. 0 NOR with 0, that is equals to 1. For 1, 0, so we have now an output of 1 for your first AND gate and 0 for your second AND gate. Since it is equals to 1, then this output will become 0. When both are 1, 1, so since this is equals to 1, the first input of your NOR, this will generate an output of your NOR equivalent to 0. So we have to determine your truth table. So when clock equals to 1. So we have a first combination of 0, 0. Your previous Q is 0. Your next Q is the same as 0. If your previous Q is 0, the next Q is the same as 0. So that is what you call your no change. Next combination is 0 and 1. Your previous Q is 0. You generate a value of 1. If your previous Q is 1, you also generate a value of 1. So therefore, we have an output of 1. If both combinations are 1, 0, your previous output is 0, then you generate a 0. If your previous output is 1, then you generate the next value of your Q as 0. So we have 0 output. And if we have this 1, 1, your previous output is 0, then it becomes 1. But if your previous output is 1, then it will become 0. So we call that one as toggle. So if your previous output is 0, then it will become 1. If your previous output is 1, then it will become 0. And this is your logic symbol for your G key flip-flop. For the edge triggered, so this is your edge triggered. So that is your output will change state only when the edge is going up. So they have the same truth table of your J key for your 0, 0, that is no change, 0, 1, that is 1, 1, 0, that is 0. If it is 1, 1, so this is 1, this 1. If it is 1, 1, then we have a toggle. Then we have your T flip-flop. So this is your T flip-flop. You have one input connected only to one input connected to your whole AND gate. So if your clock is 0 and your T is either 0 or 1 and your Q previous is 0, then the output of your AND gate are all 0. Since it is all 0, then we call that one. Since it is a NOR, so we have a no change condition of your next output. If your clock equals to 1 and your T is 0, as well as your Q previous or QP, or that is the present state of your Q, is also 0, the output of your AND gate are all 0. So we have now to determine your output Q using the previous Q. So this is 0, NOR with 0, then your Q bar equals to 1. If this is 1, NOR with 0, then your Q is equals to 0. And if we have 0 and 1, so your T now is 1. So we have now a value of 1 of your second AND gate, since Q bar is 1. So Q previous is 0, therefore Q bar is 1. So we have 1, and this is 1 and 1, so output is 1. So in your NOR gate, if we have an input, one of your input is 1, then it will generate an output of your NOR as 0. Since this is 0, then NOR it with 0, we have an output of 1. If we have 1, 0, so your T is 0, so we have both output of your AND gate are all 0. So we have now to determine your Q and Q bar, your next Q and next Q bar to your previous Q. So your previous Q is 1. So we have 1 NOR with 0. It is equals to 0. If this is 0, NOR it with 0, then it is equals to 1. And we have your 1, 1. So this is equals to 1. Since it is equals to 1, your NOR gate will generate an output of 0. So this is your logic symbol. For the edge triggered, you have this one. You have an RS connected to your clock. If you have a clock which is equivalent to 0, either your Q, P, or 0 or 1, as well as your T, 0 or 1, then there is no change. If your clock is equals to 1, both Q, previous, and T is either 0 or 1, then there is no change. If your clock is going down, if your T is either 0 or 1, or your QP is either 0 or 1, this is also no change. Going up, but both T is 0 and your previous Q is 0, so we have an output of 0 in your AND gate. Since it is equivalent to 0 and 0, so we have to determine your next output using the previous Q. So Q is 0, NOR 8 is 0, therefore Q bar is 1. If this is 1, NOR 8 is 0, then we have an output of 0. If T is 1, then this second AND gate will generate an output of 1. Since if it is equals to 1, your Q bar will be equals to 0. 0, nor with 0, then your Q equals to 1. If your T is 0 and your clock is going up and your previous Q is 1, since that is 0, so output of these two AND gate will be 0. So we have to determine using your previous Q. So your previous Q is 1. So we have 1 nor with 0, it is equals to 0. 0 nor with 0, it is equals to 1. And we have 1. If it is equals to 1, so this is equals to 1 and this is equals to 0 because your Q bar is 0. Your previous Q is 1. So the Q bar is 0. Since this is equals to 1, this will generate your burst nor give an output of 0. So this is your logic symbol. Then for the master slave, so this is your master slave, you have two RS connected in cascade with your clock connected to your AND gate and also to the second AND gate, but this time it is complemented. So this is the truth table of your master slave. It is the same as your G key flip-flop when clock is equivalent to 1. So if P and G are all X, then that is no change. If your clock is going up and your input Q and G is 0, that is no change. If it is 0 and 1, then Q is 1. If it is 1 for your K and G is 0, that is 0. If your both input are all 1, then you have an output of toggle. That is, when previous is 1, then it will make your next Q 0. If your previous Q is 0, then it will make your next Q as 1. So in the electronics design, usually outputs are given. Then the present state and the next states are known. To generate the next state, the controlling parameter must be determined. So these controlling parameters are what you call your inputs. So we have to generate what you call your excitation table. This shows the minimum inputs that are necessary to generate a particular next state when the current state is known. So for your latch, we have RS. So remember, this is your RS circuit, and we have this excitation table. So for your previous Q, it is 0, and your next Q is also 0. So by default, your R and S is at 0. So from 0 going to 0, your S is 0, and your R must be equals to 1. Or it can be also 0. So when you have a 0 for your R and 0 for your S, remember that is no change. So we have the same output from 0 going to 0. So your R is either 0 or 1. From your previous output, it is 0 and your next output is 1. So we have to make your R 0 and your S equals to 1. And from previous output, it is equals to 1 and your next output will be 0. So we have to make your R equals to 1 and S equals to 0. And if your input is from 1 going to 1, remember, if we have a 1 output, this is the combination of your R and S. So we have this combination. So what will be the value of your R and S? Since it is equals to 1, we have your R is equals to 0 because your Q is 1. We have to set your Q is 1. So R must be 0. Then your S must be equals to 1. Or your S equals to 0. So if your S is 0 and your R is 0, that is no change. Remember that your previous output is 1. So if no change, it will remain at 1. So this is now your excitation table for your RS. For your DLATs, so if we have a previous 0 going to 0, so we begin that our D is by default at 0. So if it is going to 0, then your D is also 0. If your previous output is 0, then your next output will be 1. Your D is also equals to 1. And if your previous output is 1, and your next output will be 0, your D is also 0. And if your previous output is 1, and the next output is 1, your D will remain as 1. This is the excitation table of your DLATs. For JK, we have to input K and J. So if your previous output is 0, and next output is also 0, we put first that our G and K at 0. So from 0 going to 0 for your output, your key is either 0 and 1. If it is 0 to 1, so we have to make your G equals to 1 and your key equals to 0, or we have to make your key equals to 1, because if both G and K equals to 1, you have an output of toggle. So previous output is 0, it will toggle to 1. Then if your previous output is 1, then going to 0, so you have to make your key equals to 1 and G equals to 0. Or make our G also equals to 1. So if we have 0 for key, if we have 0 for G and key is 1, then your Q will be 0. But both input G and key are all 1, it is toggle. Remember that your previous output is 1. If we toggle, because of your input are both 1, then it will become 0. Then from 1 going to 1, so your key must be 1 and your G must be equals, your key must be 0 and your G must be equals to 1. Or it must be also equals to 0, because 0, 0, that is no change. For T flip-flop, from 0 going to 0, so we first begin that your T is at 0. So going to 0 from 0, your T must be 0. If it's going to 1, T must be 1. And if it's going to 0, your T must be 1, because it is toggle. If it is from 1 going to 1, then your T must be 0, because it will remain on the value of your Q, which is equals to 1. So this is an example how to determine your output Q. So this is your input R and S, and this will be your output if your R and S is a label triggered latch. And for D, this is your input for D. Then we have an output Q if we consider that we have a label D. And T, this is your T, and we have an output of your T if we consider that one as a label T. And we have also this input G and key, and we have an output HQ, meaning your G and key is an edge triggered. So this is an output of your edge triggered G key. If you have this D and your D is an edge triggered, so this is the output of an edge triggered D. Then T input, and this is the output of your T if it is an edge triggered. And that's all for our storage element.